Hi, Maggie. Just to let you know, too, there's about a 10 to 15 second lag between what I see on the screen and what ends up coming up. So there's about, hey Josh, how's it going? Glad y'all found it. I had a little bit of a hiccup getting it to get a link that would work, but glad you guys found it. So you guys have any questions for me? You can just use the chat if you like. Like I said, there'll be about a 10 to 15 second lag or so between what you do and how long it takes me to react to it. Just so we'll have to be patient with one another, I guess. So if you want to just type your questions in chat, I'll start answering them. Okay, so Maggie's asking if I could talk a little bit about what the classical potential is and how it relates to the Schrodinger equation. The classical potential is just the potential energy function. So for instance, we're going to eventually be talking about the harmonic oscillator. The harmonic oscillator potential is 1/2 kx squared because it's just a mass on a spring. So that v sub x function there is the potential energy that's associated with whatever forces the quantum are experiencing. So, for instance, also the particle in the box problem that we're doing also is there's no potential in the region inside the box, and then the walls of the box have a potential which is infinite. So that potential energy means that there's no kinetic energy that would allow it to escape outside of the box, because that represents the walls. There's this infinite force at the walls represented by the infinite potential energy that it would have there. Does that help? I'll pause and see if that's helpful at all. Okay, let me look at question 6.3. I've got the book right here, just to remind myself about it. Okay, so in that problem, what it's asking you to do is use the Schrodinger equation with that particular wave function. So take the Schrodinger equation with that wave function. The first part of the Schrodinger equation is the derivative part. So the Schrodinger equation, I guess I'll write using my very sophisticated paint. All right, negative h bar squared over 2m times the second derivative of psi with respect to space plus v of x, okay, that's what you're going to be looking for, times that psi is equal to v psi. Okay, so what you'll want to do is they give you the wave function for the particular solution they're talking about, and you can plug it in here, and then they're giving you the energy. So by taking the derivative and plugging in the energy that they give you, there might be a way for you to figure out what v sub x was. Does that make sense? And I'll pause to let you answer. Sorry about the lag again. I'm looking at it now. I see you're asking about part B. Part B is asking you to sort of dig back into your memory, and is there a potential energy that has this x dependence that you've seen before? And I might have mentioned mentioned it earlier on when we were talking about the classical potential in general. I don't want to be too cryptic, but one that goes like, for instance, 1/2 kx squared is the classical harmonic oscillator potential. If it was something like a constant times x or something like that, 1/2 kx squared. It doesn't. You might not have the k. It might not be exactly the k, but I'm just seeing your second comment or your third comment now. If it goes like x squared, then it is then it has the same x dependence as the harmonic oscillator potential, or the mass on a spring potential. If it was linear in x or y or whatever you wanted to call it, then that would mean it would act kind of like gravity does, because that's like m times g times y. It would be a linear function. But the potential energy that goes like x squared or y squared or whatever variable squared, position squared, that acts like a harmonic oscillator. Does that clarify? It's just asking you to recognize it. Okay, sure. Any others? I guess it's going to be a little bit quiet here. Folks don't ask a lot of questions, but would it be useful for you for future ones of these that I have a little bit of something prepared to talk about, like maybe looking at more of the example problems, or leaving off an example, or having an example problem sort of prepared and ready to kind of go through, and then I can take questions as we go through that? Would that be more useful? Okay. I think I'll try to have something prepared for next time a little bit more. Were there any questions on the examples that I had in the lecture notes? Did you want to see me go through the particle in the box solution? I tried to make it as clear as I could in the lecture notes that I put together, but maybe it helps a little bit to have maybe to see it as I do it rather than just have it all laid out in front of you directly. Do you want to see the particle in the box or something like that? Okay, I just saw Maggie's question about the wave function of a free particle. So let's do that. All right, so our Schrodinger's wave equation is this expression here, which I already have on the screen. For a free particle, the potential is 0 everywhere. So what if Vx is 0 for all values of x? So that's the free particle. Okay, so if that's true, then this term is 0. Okay, it doesn't matter what psi is, it's going to be 0. And then it's a differential equation in psi that is just a nice, relatively simple one. So if I rearrange this expression a little bit, I get the second derivative of psi, okay, is equal to, okay, negative. So I brought the negative sign over there, and we got 2me over h bar squared times psi. Okay, so I just saw another comment by Maggie. I want to see if I address it. I guess why does that part of the equation get set equal to e psi? So that I guess that's just part of the Schrodinger equation here. If you can see the Schrodinger equation, if v is equal to 0, we can rewrite it as this expression here. And now it's just a matter of solving for psi. And it's a second order differential equation, but basically it's saying take the derivative of psi, do it twice. Take 2 derivatives of psi. When you take 2 derivatives of psi, you get psi back with a minus sign in front of it with a bunch of constants in front. So it's some negative number times a constant times the original function back. And we know what that would be. We know a function psi that satisfies that. There's a couple of different ways to write it. I said, well, you could write it as psi is equal to a sine function. It could be equal to a cosine function. It could be a linear superposition of those two together. Or we could write it as a complex exponential. So I'm just going to write down the complex exponential because that's the solution I chose to use. So psi of x is something like e to the I times k times x. Okay, I'm not saying what k is here just yet, but I think you'll notice, and I'm going to put an a in front of here just as an f, because it's any constant times that would also do. Okay, so now if I look at this and I say, well, let's imagine I was going to take the second derivative of this function. What would I get? I would get, well, if I take the first derivative, I get just I times k times a times e to the ikx again, because that's what exponentials do. Now take the derivative again, and I would get another factor of I times k out in front. Well, 2 factors of I, that's I squared, that's negative 1, because this is a complex number. This is the imaginary number. So then you would get negative k squared times a times e to the ikx, and you get the same function back with a negative constant in front of it, which that happens to work here. So this works when k squared is equal to 2m e. Whoops, that's supposed to be an e. Imagine it's an e over h bar squared. And then that works. It works if this is true. So a sine or a cosine or a complex exponential all give sort of the same result, that when I take the second derivative of that function, I get minus a constant, or a constant squared, whatever, constant squared, same thing, times the original function back. And this is an expression then that says, well, this is the wave function that works for a free particle. Okay? I'll pause and see if that's okay, or if you have a further question on that, either Maggie or Josh. Okay, thanks. Anything else? I guess I'll ask too, how far have you got through did you get through the second set of lecture notes yet? Or not set, the second lecture notes, the ones that we're going to be due for, or that you were supposed to look at for today, potentially, or possibly. On operators and expectation values and stuff like that. Did you have a chance to look at that yet? I guess I'm going to erase this while I wait for responses. Okay. Well, maybe I could talk. I don't know if Josh had a chance to look at them yet either, but I could talk briefly then about what the wave function means, some of the ideas about that, so that you can sort of have a sense going into that second set of notes, if you haven't looked at them yet, a little bit of an idea what's going on with that. So, okay. I just saw Josh he's only had a chance to skim over them as well. So let me talk a little bit about those so that you can have a little bit of an idea on those. The idea in that second set of notes is that we're going to be talking about operations and operators and the idea of expectation values and the interpretation of the wave function. So one example that I put out there, which I think is relatively interesting, is that there's a wave function. So first of all, let me describe a baseline. First of all, the wave function of the simple harmonic, or not the simple harmonic oscillator, the a particle in the box is this. So if the box has a size L, it has infinite potential at 0 and infinite potential at L, and 0 from between 0 and L, and the particle is constrained to be between x equals 0 and x equals L, and its wave function is going to look like this, it turns out. And this was one of the things that we did for the first set of notes. So that is the set of wave functions for a particle in the box. Notice that there's a whole bunch of different functions that work here. For every value of n, the wave function is a little bit different because this basically tells you how many bumps there are in the wave function. You know how many, because that value of n tells you how many sort of antinodes there are in the box. So when n equals 1, which is the one with just one peak in the box, that's one version. But another one that also works is 2, and that's the wave function where it looks sort of like, that's x equals 0, or psi equals 0. It goes up and down, and then it's 0 at the endpoints again. It still works, but there are 2, but 3 also works, and 4 also works. So n is any integer, and those wave functions, they all work. They all produce a situation where we've got the particle is in the box, but there's a different energy associated with each one of those wave functions. For n equals 1, there's a particular value of the energy. For n equals 2, when the wave function for the particle is different, it turns out that corresponds to a higher energy, a higher energy state. So the lowest energy state happens for n equals 1. The first excited state is what we call it, is n equals 2. That's when the particle's wave function, whatever that means, is it's got 2 bumps in it. It's got a peak and then a valley and then reaches 0 at the ends. And then same thing for 3. But they all have different energies. So there's a wave function associated with each individual energy. And what we call those wave functions, then we call them eigenfunctions. Eigen is a German word for particular. And they each have an associated energy with each one of them. So that's the eigenvalue problem. The energies are the eigenvalues, the particular values of energy that go along with the particular wave function that has the same n associated with it. Okay, so I'll pause there and see if there are any questions about that idea. Okay. Well, Maggie says it makes sense so far. I think, let's see if I can remember off the top of my head. I should look at this, but the energy associated with wave function number n is n squared, pi squared, h bar squared. It's supposed to be h bar. I'll make it a little better. All right, there we go. Over 2 m l. Okay, so that's the energy associated with the nth wave function, which solves the Schrodinger equation. Now here's the thing. We know that from general differential equations, which you're all experts in that now. I don't know if you're experts, but you've had some experience. That if you take 2 functions that are each individually a solution to a differential equation, if you add those 2 solutions together, it's still a solution of the wave equation. So here's the thing about that, though. Let's say that instead of having just one of these, I'm going to have a mixture of 2. Okay, so this is what I'm going to do. I'm going to say that the overall wave function psi x is actually a sum of 2 different wave functions with different ends. Okay, so this is what I'm going to do. I'm going to say, all right, it's equal to square root of 2 over L. That's a common factor, and I'm going to... Okay, and then I said there's a weighting function here that I'm going to... Okay, so this is an example problem from the second one. Oops, that's supposed to be a square root. We'll get the area. And then I'll put this one in here. Sine of 3 pi x over L. That's supposed to be an x there, but hopefully you see. Alright, so something like that. Alright, that's a big parentheses there surrounding the whole thing. Okay, so let's say this was a wave function. Notice that it's a sum of, I've got the common factor of square root of 2 over L, which is common to all of them, so I just brought it outside these parentheses. And then there's a coefficient times the wave function pi x over L. Now notice, that corresponds to the wave function where n is equal to 1. And then there's this other factor, coefficient out front of a different sign, but this one's 3 pi x, that's supposed to be an x, hopefully you can see that's an x right there, 3 pi x over L. So this is the part of the wave function that looks like when n is equal to 3. The thing about this particular wave function, that it's not, or this, the one that I've written down here, is not just, it's not a value where n is known. It could be one of two different values. It could be either n equals 1 or n equals 3. So this gets to the idea of Schrodinger's, almost like the idea of Schrodinger's cat. If I ask, you may have heard this sort of story about Schrodinger's cat, where is the cat, the cat is inside of a box, and there's poison inside of the box, and there's a kind of a randomization thing, and there's like a 50% chance that poison has been released and the cat has died, but there's a 50% chance that the poison hasn't been released and therefore the cat is alive. And then we ask the question, what's the state of the cat? Is the cat alive or dead? And Schrodinger's response to that would be, well, it's in a state where the cat is, we don't know whether the cat is alive or dead specifically because it exists in two states. There's a 50% probability that the cat is dead, and there's a 50% probability that the cat is alive. This is sort of the same sort of representation for that, but not a biological system, in a system with the particle in the box. If this is the wave function of the particle, there is a certain percentage chance that the particle has n equals 1, and there's a certain percentage chance that the particle has n equals 3. And the percentage chance is actually the square of the coefficients sitting in front of each of the parts of the wave function corresponding to each one. So, if I were to ask you, what is the energy of this particle? You couldn't say definitely it was energy corresponding to n equals 1. You couldn't say either, also you couldn't say specifically that it was n equals 3. You know it's one of those two energies. But if you were to make a measurement, the chances are 2 out of 3, the square of this coefficient right here, that it would be, the energy you would measure would be equal to n equals 1. And if you were likewise able to make another measurement and you would say, well, let's measure it again, there would be a 1/3 probability, the square of this coefficient here, that the number that would come out would be correspond to the energy associated with n equals 3. And that's the proper interpretation of a wave function. If you have a superposition of different eigenfunction states, this one n equals 1, this one n equals 3, that superposition, the coefficients of that superposition tell you the probability that any one state would be measured for that particular energy or any other observable that you're talking about. So I'll pause there and see if there are questions on that idea. So I'll write, while I'm waiting for questions, I'll put a little bit of a mark in here that this That'd be 2/3 probability. You square that. So I'll put probability or prob. 2/3 for that one. 1/3 for that one. So there are no questions on that? If there are no questions, then just put no questions, because otherwise I can't tell if the stream was interrupted or something like that. Or maybe you're stunned. It doesn't make a lot of sense. You're not even sure what to ask. Okay. So hopefully that gives you sort of a sense that you probably heard the idea of Schrodinger's cat, and maybe this gives you a sense of what that really means. I mean, and why he was talking about it in those terms was just to try to sort of simplify it. But this is when it gets, the sort of the rubber hits the road. It's like we've got a real, this is sort of a relatively realistic problem where that idea of probabilities fits in. So if I were to ask what is the average energy, if I would make a measurement of the particle in this quantum 1,000 times, then and say, well, what's the average energy that we get out of this? Just on average, what energy would we get? Well, what you'd do is you'd say, well, I've got, and this is an example problem at the end, and there's, in a sense, there's more involved than what I'm talking about here, but it reduces to what I'm going to say. The problem asks for what is the average energy that's received here. And the answer to that is you're going to have to take a weighted average. 2/3 of the time you're going to get the energy associated with the n equals 1 state of the system. So it would be 2/3 of the time you're going to get n equals 1 here, and you'd get a value of pi squared h bar squared over 2ml squared. But 1/3 of the time you're going to get a value of where n is equal to 3, which would be 9 pi squared h bar squared over 2ml squared. So if you take a weighted average of that, you'd say, well, 2/3 times energy 1 plus 1/3 times energy 3, add those together, and you get the average energy that you will get. Now notice that average energy that you get is not equal to any of the two possible values that you get. It's not equal to the n equals 1 value of energy, and it's not equal to the n equals 3 value of energy. The average energy is going to be somewhere in between. That will never be a value that you would ever measure, but it would be the average over many measurements. And that's what we call the expectation value. It's the average energy over many, many measurements. It's kind of like if you were to take a measurement of the diameter of a quarter, and say you got micrometer, so you're using it. Let's say that you take two measurements. One of them is you got, I'll say it's 1.3 centimeters, and the other time you have 1.5 centimeters, and that's it. That's the only two measurements you took. What's the average of those two? Well, it'll be 1.4 centimeters. But notice that neither one of the values that you measured was actually equal to 1.4 centimeters. It's the same sort of thing here. Okay, hopefully that sort of makes sense. I'm going to erase this and ask for more questions then, I guess. So I'll talk a little bit about what an expectation value is from a mathematical standpoint. I just talked about it conceptually. But, hi Melissa. So let's say that I was going to do something like this. So this is the expectation value symbol. Let's say that I wanted to know if I had I want to know what the expectation value of the horizontal position squared of the particle. Okay, so that's kind of a crazy thing to ask yourself, maybe, but let's say that that's something that you wanted to know. What's the square of the horizontal position, the x position of the particle? Okay, and this is what you would do. If the particle is in a particular state represented by the wave function, this is what you do. You take the integral. This is the definition, the mathematical definition of this. You're going to take the integral over all space. So I'm going to say, for our purposes here, that's between, because we're being real general, from positive infinity to negative infinity. Okay, and let me state this as well. This is over all space. Now, for the particle in the box, the wave function is 0 for values of x that are less than 0, and it's also 0 for all values of x that are greater than L. So actually, the integral that you would have to do for a particle in the box is only from 0 to L. You don't have to go all the way from minus infinity to plus infinity. It's equivalent because you'd just be integrating with an integrand which is a bunch of zeros for all those things that aren't between 0 and L. So this is still true, but it's not. This is just as general as we can make it. Okay, so what are we going to take the integral of? This is what you're going to do. You're going to take the integral of psi star. Now, what psi star is, it's the complex conjugate of psi. Now, the complex conjugate is just wherever you see the imaginary number, put in negative I, minus the imaginary number. That's it. That's all it is. That's a complex conjugate. Very simple. A lot of our wave functions could have an I in it, but some of them don't. For instance, the particle in the box problem that we were just talking about, notice that wave function that we wrote down didn't have any I's in it. Didn't have any. So psi star is just the same thing as psi if there are no I's, if there are no complex numbers, imaginary numbers in it. Okay, so it's psi star of x, and then in between that you put the thing that you are, whose expectation value you want to know. So you put x squared in there. And then you multiply it again times psi. Okay, now this is regular psi, not complex conjugate. And then you're just integrating that over everything, all positions. Now, if psi is represented as a function of x, then you integrate over all possible values of x. And you just do that integral. That's it. That's the expectation value of x squared. Okay. And that's the definition. All right, now, the thing about this is, sometimes this quantity right here can be an operator which does weird things to the wave function. So, for instance, what if instead I wanted to know the momentum? And I'm going to put a little hat on top of the momentum there to indicate that this is an operator that needs to be distinguished from just the value of the momentum. Now, in quantum mechanics, I'm going to write down, just put a little note down here just so that we can see it. The momentum operator is equal to not just a number, it's actually an operation. It's negative I times h bar times the derivative with respect to space. Okay, now that means that when I would do this operation here, this would be equal to, again, the integral over all space, minus infinity to plus infinity. Okay, we got psi star here again. Okay, so again, whatever wave function you have that's involved here, take the complex conjugate of it, and then again we put the operator in here. Now before that was x squared, so it was really simple. And you could, since it's just a number, you could bring it out in front. There's no problem with that. But with a momentum, now we have to do an operation. On the wave function. Okay. So now what this is actually telling us to do is take this derivative of psi, because that's what, just link that up right there. I'm going to take negative I times h bar times the derivative of psi with respect to x, then multiply that times the wave function's complex conjugate, not differentiated, and then that whole quantity there, our new integrand, that is what I'm going to integrate from minus infinity to plus infinity. And that would give me, once I complete that integral, I would get the expectation value of the momentum of the particle that has a wave function given by psi. Okay, I'm going to pause and see if there are any questions on that idea. If you don't have a question, just say it makes sense or no question, just so I know that you got it or you're willing to accept that. Okay. So sometimes these integrals, so I'm seeing now on the stream that folks are saying no questions, so that's good. I'm glad that's true. Sometimes these integrals can get a little hefty. And I made reference to that in the second lecture notes. Like, to do this integral, for instance, for the particle box, involved, just to tell you what that I've been having a little bit of challenge with this too. I brought my work home last week and I was working on those lecture notes to make them understand what I thought was going to be a little bit more understandable. And I didn't bring my integral table home. So I had to do this integral by hand for the size, sine of n pi x over L or pi x over L or whatever it was. And I gave you a hint, it takes like a U substitution, integration by parts twice, and recognizing a loop. a looping method of integration. So some of these integrations are not trivial, but you don't have to go through the pain that I did because I forgot my integral table. If you can integrate it using your calculator or some other means, whatever it takes, I don't care the method you use to perform the integration if you have to do it. What I care about is that you're setting up the integral and being able to interpret what the answer is once you get done with it. So I'm not asking you to remember your integration by parts and all that stuff. As much fun as I'm sure it is for you, it's you don't have to do it. The other thing that I'll mention on this is that this operation here, this finding the momentum of this particle here, of this state here. So let's say I have a particular value or I have a particular wave function here. So let's say that my wave function is the square root of 2 over L. This is just an example. It's not always going to be this, but let's say it's the particle in the box, and let's say it's in the n equals 1 state. So that's with, it says n pi x over L, so our n is going to be 1. So it's pi x over L. Okay, so let's say that's psi. Okay. So the eigenvalue, the generalized eigenvalue problem is the following. It says that if you take an operator, a generalized operator like our momentum operator, and if you multiply it and you operate on the wave function that you're talking about, that should be equal to some constant, which I'm going to call p, which is it's the momentum associated with it, times the function back. Okay, that's the general eigenvalue problem. It says take the operation here. If you operate on a wave function and a particular function, if you operate on that function and what you get back when you perform that operation is equal to some constant. Now p here represents a number, not an operation, but a number, times the original function back, then that function that we just talked about that you operated on must be a eigenfunction. And the value that you get out would be the eigenvalue that's associated with that eigenfunction that makes this true. Okay, so I am going to demonstrate something about the p operator here, and oops, I need to delete more. Okay, so let's take this problem right here, and let's use this operator right here for a momentum operator. So if this is our momentum operator, we got negative I times h bar, okay, times, now let's take the derivative of psi, okay, so here's psi, pi x over L. All right, here we go. Okay, so this is the left-hand side of this little eigenvalue problem. Well, let's do that. Negative I times h bar. All right, take the derivative. What do we get? Well, I get the square root of 2 over L, no problem. We just bring that out. Now, take the derivative of this with respect to x. You get pi over L times, now what happens? Okay, when I take the derivative of sine, what do I get? I get cosine, don't I? So that pi over L comes from the chain rule. Oops, cosine, there we go. Okay, now I perform the operation. Now, if this is the standard eigenvalue problem, I'm going to say, all right, is that equal to a constant times the original function back? Now, p is the constant that would be the eigenvalue here. Is this equal to some constant p times the square root of 2 over L times the original, here's our original function, pi x over L again. That's an x. There we go. And the answer is no. It's not equal to a constant times the original function back. The operation that we performed here to get, the momentum operator, when it operates on psi, it changed the sign into a cosine. That's not the same function. What does that mean? The interpretation of that is that the wave function that we just put in there is not an eigenfunction of the momentum operator. And in other words, that means that this particular state does not have a definite value of momentum associated with it. If it did, we would have got the value of that momentum times the original function back. It's not an eigenfunction of momentum. We do know, though, that it is an eigenfunction of energy, because what we talked about earlier is if you take the energy of this thing, every wave function has a particular energy associated with it. The eigenvalue is the energy. Okay, so the harmonic oscillator, or not harmonic oscillator, the particle in the box, wave functions are not eigenfunctions that have a definite momentum. They do have a definite energy, but they don't have a definite momentum. The momentum would be uncertain. Okay, any questions on that? I'll pause and take questions on that. So I'll show one other thing about this, just so you can kind of see it. And this is, it's not, it's a little bit of a, I wouldn't say it's a review, but it's just to give you a little bit of a thought about the idea of eigenvalues and stuff like that. The energy operator associated with the particle in the box. This is only for a particle in the box. Oops. Second derivative. That's the energy operator. Now, let's test that statement that I made earlier, that this is that this wave function here would be an eigenvalue of the energy operation. So that would say it should look, the general eigenvalue problem associated with this was energy would be that the operation, the energy operator acting on psi, the wave function, should be equal to some constant value, E, which I'll call E, times the original wave function back. Okay, so let's do the energy operation on this. Now this one isn't so bad. We've got, when I take the derivative of this once, so I'm leaving out the coefficient here for a second, but let's just focus on the derivative. Okay, if I take the derivative of this once, I get a factor of pi over L, and then the sign turns into a negative cosine. Then if I take the derivative again of this thing, I'll get another factor of pi over L, and I'll get negative sine. Okay, so overall then what I'm going to get is I'll have the overall operation then is I've got h bar squared over 2m. The minus sign from here will exist, but also when I took the derivative of the cosine to get negative sign, there'll be another minus sign there, so I'll get a plus. Okay, that should be a... Imagine. Let's see, what should I do? Maybe I can erase. I'm going to try it. Look at that, just like a pro. Okay, now I want to draw. Do I have a brush? There we go. All right. So there we go. I've got h bar squared over 2m. Now, remember I had two factors of pi over L. So that's pi squared over L squared. Okay. And then what did I also have? What did I get back? I got, well, I still have the square root of 2L running around over there. And remember, I got my sign after I differentiated it twice turned into a negative sign. Couple of that minus sign gives me my plus. I get the sine of pi x over L. Okay, so that's what I get. Now, I'm asking myself, is that equal to some constant e times the original wave function back? And again, just like before, I'll put a little question mark there. Does it work? And it looks to me like it works, doesn't it? What's my constant? The e looks like what I just put in parentheses there. E is equal to h bar squared pi squared over 2m L squared, which you will notice if you look back at the energies associated with the particle in the box. This is the energy associated with n equals 1, which is no coincidence. This is the wave function that corresponds to n equals 1 for the particle in the box as well. So it is an eigenvalue. This wave function is an eigenfunction, a particular function of energy. Has one particular energy associated with it. But it does not work for momentum because I don't get the function, same function back. Okay, so I'll pause and see if there are any questions on that. Does that, hopefully that's sort of connected how it could be an eigenfunction of one operator and not of another. Okay, so I'm seeing it. Maggie says makes sense. I'm glad. I'll just, there's one thing I'm going to look in the book right now. I know there's a problem at the end of the book. It's that I'm assigning you. It's number 56. It's out of the second problem set, and it's rather long. But I mean, the writing is long, so it takes a while. But let me just talk briefly about that problem, because you're going to have to solve the particle in the box problem for a different set. So let me talk a little bit about that so that hopefully it makes as much sense as I can make it. So the original particle in the box problem, we're really focusing on the particle in the box now because it gives us so much. We get a lot of mileage out of looking at it because we can kind of understand what it means physically, but we can use that since we understand the classical physics of a particle in the box well enough. It serves as a good sort of springboard to talk about, well, what's different in quantum mechanics compared to classical mechanics. So the particle in the box from our point of view was the one that we solved was this one, where the potential energy as a function of x looks like this. So at x equals L, v is equal to infinity, and at x equals 0, it goes up to infinity as well. It's just, so the particle, there's v's equal to, it's supposed to be a v, infinity at that spot, and up there at x equals 0 as well. That's the particle in the box that we've been solving. And then we did solve, and so the problem in 56 is to change that situation a little bit so that you have a chance to solve the problem sort of on your own. So it's not really on your own because they give you a lot of ways to, a lot of things to think about. So what they're saying is the following. The potential energy now, instead of being, going from 0 to L, it goes from negative L over 2 to positive L over 2. And these are the positions. Where v is equal to infinity. Again, it's a particle in a box. But now it's a symmetric box around the origin. This is v as a function of x again. And it asks you to think about how the solutions would look different if you change the geometry just a tiny little bit like this. The box still has a width of L, but it doesn't go from 0 to L, it goes from negative L over 2 to positive L over 2. And what it says in there is this potential is symmetric about the origin, which means if I look at the right-hand side and the left-hand side, they look the same. What that means for the wave function then, because the way the Schrodinger equations, the wave function for the Schrodinger equation works out, if the potential is symmetric about the origin, then there's nothing different about the right half of the box as opposed to the left half of the box, which means that the particle, the probability that's associated with the particle, which is equal to psi, the absolute value of psi squared, that should be symmetric around the origin too. So if let's say there's if there's a 50% probability that the particle exists over here, there better be a 50% probability that's over here. If at this spot right here, there's a little spot right there, just between there and there, which is a particular distance away from the origin, if there's a certain amount of probability that it lives in this particular x position there, then the same distance away from the origin on the right-hand side, it better have the exact same probability there. So it's saying that the probability distribution needs to also be symmetric around the origin. That's what it's saying in the first part. So the probability distribution function, the probability which is equal to the square of the absolute value of the wave function, that needs to be symmetric here. And that hopefully gets you thinking forward about how this would work. Because of the symmetry of the potential, the probability has to have that same symmetry. Does that make sense? I'll pause then to see if that makes sense for folks. Okay. All right, well that should at least get you started on that one. That one's a little bit of a heavy lift. I'll keep an eye on the discussion boards here as well on that one too, in case there's any questions on it. Do you have any more questions for me? We've been going a little over an hour here, and I don't want to take up your whole day here. But if you don't have any more, if you do have questions for him, now's sort of the time to ask. But if you don't, I guess we can end it here, and this will be posted so you can look back at it if you need to. But I'll pause now and just ask if there are any other questions on homework problems or anything like that that you need work on or need some answers on. Okay. Maggie's got a question about the feedback on homework assignments. So I'll make the feedback to your homework assignments available later on this week. So you should be able to see it there at that time. So I've been struggling, maybe like you have. The last couple of weeks I've been working to get the course kind of put together. Hopefully, now that I've got a little bit of a rhythm to making that work, I can make your feedback available there. So I would look for that by Friday. You should get your get feedback on some of those homework as I post those grades up. And then I'll leave a little link about how. Not yet, because I haven't put the old assignment feedback in yet. And I'll start putting those in probably tomorrow so that you can see how it looked. So sorry about that. I was behind before spring break hit and this stuff hit, and I'm still behind, but I'm catching up. And I do have your exam grades done for the for exam 2, and I'll post those later on this afternoon. Any other questions that I can answer before we call it? Yes, I will. That's a good idea, Mel. I will post a key to the second exam. If you would please not share it though, just because that's why oftentimes I'm perfectly willing to post or to work out examples in class and stuff like that, but I generally don't like to post solutions to things because it ends up getting out into the public domain, or it can get into the public domain. This is a small enough group where I'm not too worried about that, but please don't put it into the public domain if you would. Of course, you're welcome to use it, for your own studying and stuff like that. But you don't have to answer to that. But yeah, I can do that. Let me make a little note of that for myself. So I wrote on the wall. All right. Any other questions that I can answer? Okay. All right. Well, I'm happy you all were able to attend. I will mention this. I know it's a little bit annoying with the delay that we have here with the stream. The value of it, though, is that I'll be able to post the stream. If we had used Zoom meeting or something like that, which is a little bit better for back and forth, that allows you to be back and forth really well. The problem is that it's not quite so easy to post an hour-long video that you recorded of it. So this is nice in that although there's a delay, you have the stream is immediately available on YouTube, and I'll give a link to it. So if you want to go back and look at what I did, or see what we talked about, or for those that missed it, for instance, they'll be able to view it as a video from the link that I'm going to give on the D2L site. So, okay, if there are no further questions, then I think we'll end it here. Next week we'll have a stream same time, I think. If you would like the stream to be at a different time or a different day or something like that, feel free to leave that as a note on the discussion board so that we can kind of get, so I can make sure that everyone's able to attend that wants to. Okay, so I think we'll end it there. Thanks for your attention. Hopefully things are working out. Post questions to the discussion board if you have questions on more of the homework problems, stuff like that. Okay, have a great rest of the week, and we'll see you next week, if not before. Bye now.